We're going to do one more derivative example using the limit definition, and then we'll be done with the limit definition for a while, but we'll come back to it in the weeks ahead. This one is a square root function. So we've got the function f of x equals the square root of x plus 16. Don't be tempted to distribute that square root, right? That's not the same as saying square root of x plus square root of 16. Square roots don't work that way. If you try to plug in some number like 9 for x, you'll see that you don't get the same answer. So what do we got here? We use our normal derivative definition. Again, I would suggest that you try to put in the h right now. Make sure you get in the right place before you watch me do it. So this function's job is, whatever you feed it, it adds 16 to it and then puts the whole thing under a square root. So if I feed it x plus h, it's going to add 16 to what we fed it and put that whole thing under a square root. Minus f of x, square root of x plus 16. All over h. Now what? As we just discussed, there's no way to sort of distribute the square root over the 3 different terms or the 2 terms. So what are you thinking about doing to simplify this? I think what you would like to do is somehow get the square roots to go away, right? So often when there's people in the room, somebody will suggest that we square everything. And just to keep in mind, if you square this side, you've got to square the other side. So now you've got f prime squared on the other side. That would be okay. It would just mean at the very end you need to take a square root. But if we square this, is it really going to do what you want? Is it really going to get rid of all the square roots from the numerator? And sadly, it's not, because if you have something of the form a minus b and you square it, yes, you get an a squared at the start and a b squared at the end, but in the middle you get a minus 2ab, right? And those are going to have square roots in them. So that's not quite what you want to do. Squaring this whole thing isn't going to accomplish what you want. But once upon a time when you were studying algebra, you learned about something called the conjugate. And the conjugate of a difference like this is where you replace the minus sign by a plus sign. So we're going to multiply by the conjugate here. And as was the case with the common denominator, multiplying by the something on the top, we've got to multiply by it on the bottom. So this is another example of where we are multiplying by 1 in a clever way. So if you had forgotten all about the conjugate, don't feel bad. You probably saw it once a long time ago and you haven't seen it since. But this is what we need to solve any one of these derivatives with a square root in it. So now what happens when we do this? Now on the top, I multiply these 2 terms together. The square roots go away. So we get an x plus h plus a 16. Then when I multiply this term by this term, I get exactly the opposite of when I multiply these 2 terms together. So those middle terms cancel out because we changed the minus to a plus when we multiplied. So just to say that again, the product of these 2 terms is the negative of the product of these 2 terms. So they all cancel perfectly, and all that's left is to multiply these 2 terms together. So minus, parentheses are important, of course, x plus 16. So I think at home you were hoping to get rid of the square roots on the top, and you've succeeded by multiplying by the conjugate. Of course, you've introduced square roots to the bottom, so it's not apparent that this is going to be a good thing, but you can trust me, it is. Because what are we always hoping for on the top here? We're always hoping for everything that doesn't have an h in it to cancel. And look, that's exactly what's going to happen. The x's cancel, the 16s cancel, and the only thing left on the top is just an h. So remember, if you're ever doing one of these problems and you get to a point where you have canceled as much as you can on the top, and you still have some terms in the top with an h in it, that means something has gone wrong and you shouldn't try to go forward. And you'll notice that we're choosing particular types of functions. And you might be saying to yourself, well, this is the last example of one of these limit definitions. How come you haven't done any with this type of function or that type of function? And it would be a good exercise for you to try those functions on your own, because we're eventually going to have to deal with them when we come up with all of our derivative shortcuts, talking about log functions, trig functions, exponential functions. Try to play around with that, and you'll discover that things don't work out quite as cleanly as the examples that we've chosen for you so far. But don't worry, we'll get to those in the end. For now, we're only going to give you ones on homework and exams where it does work out nicely. So what goes here? The h's cancel. Lovely, just how we always want it to be. And when that h cancels from the top, remember there's a 1 left over. It's not like there's just nothing on the top. And on the bottom, we have square root of x plus h plus 16 plus square root of x plus 16. And so now we're not in danger of dividing by 0 anymore because that h is gone, so we can let h go to 0. Nothing changes in the top because the top doesn't have any h's in it. When h goes to 0, x plus h plus 16 just goes to x plus 16. So we get square root of x plus 16. And this one doesn't have any h's in it, so it just stays square root of x plus 16. And if you want, you can clean that up a little bit and write it as 1 over 2 square roots of x plus 16. So that tells us the slope at any given x value that we want to plug in. And the key was the conjugate. And anytime you see a square root function like this is the trick. Usually there's a saying in math, the first time you see something, it's called the trick, and thereafter, it's called the technique. So for me, this is a technique because I've seen it so many times. If this is the first time you're seeing it, it's a trick, but from now on, for you too, it will be a technique. And let's do one more tangent line. So let's find the equation of the tangent line. And let's pick an x value where things work out pretty cleanly. Say x equals 9. So I'm going to go over here to x equals 9. If we think about the graph here, what sort of number should we expect for the slope of the tangent line? We should expect a positive slope, right? If I draw the nice tangent line that just grazes the curve there. So let's see if we get that. So we want something of the form y equals mx plus b. So the slope, and I hope you're being impressed with yourselves, right? Just a short time ago, you could only find slopes of lines. Now you have found slopes of a parabola, of a rational function, and of a square root function, right? You now know how to find the slope of this curve at any point at all. That's great. So the slope at x equals 9 is f prime of 9. So we're going to plug 9 into our function up here, our derivative function, as we've named it. Nice how this worked out. Since we chose 9, we get the square root of 25, which is just 5. So that's 1 over 2 times 5, so 1/10. So now we know that y is going to be 1/10 x plus b. I think 1/10 makes sense. This seems like it's not a very steep positive slope here. And now we're in the same situation where we were before. We know what the x value is that we want to plug in. We know that this point is 9 comma something. 9 comma what? So when x equals 9, how do we find the y value? Same as it was in the last example. We plug back into the original function over here. So y equals f of 9, which is the square root of 9 plus 16, the square root of 25, which is 5. And I hope we convinced you on week 1 that the square root of 25 is not negative 5, right? Otherwise, square root wouldn't be a function. If you think that the square root of 25 should be plus or minus 5, then you should have been objecting when I drew this graph, because you should have been saying I want to be drawing a negative part of this graph as well. But that means then you're drawing something that's not a function, and this is supposed to be a function. So what do we do with this? So that means that for y, I'm going to plug in 5. 1/10 is my slope. X is 9 plus b. And this is 9/10. Y is 50/10. So I think this is 41/10. And if you want to write that as 4.1, that's perfectly fine. Thus, we have our final answer. Y equals 1/10 x plus 41/10. So where the tangent line crosses the y-axis is 41/10. And just to confirm, where did the actual, I guess we should have filled this in here. We figured out that when x was 9, y was 5. Where did the original function cross the axis? That would be if we plugged in 0 for x there, we get the square root of 16, which is 4, which you can confirm is not the same as 41/10, is a little bit less than 41/10. One last thing to mention about this. Usually when I teach this with people in the room, as soon as we write this, and it seems like I'm ready to go on to the next line, a bunch of hands shoot up and say, you're writing something with a radical in the denominator. You're not supposed to write a radical in the denominator. Why aren't we supposed to write a radical in the denominator? Whoever said that and why did they say that? And does it matter anymore today? Does anyone know why you don't write radicals in the denominators? Or why you used to not write radicals in the denominators? Maybe some of you know. So in the old days, if you had a fraction like 1 over the square root of 2, you might want to rewrite it as square root of 2 over 2. And the reason was that back then, before we had calculators, people knew things like what the square root of 2 was. So they knew that, for example, the square root of 2 was 1.4142135 something, something, something. So if I wanted to take 1 over the square root of 2, I have the choice. I could rewrite this as 1 over 1.4142135 dot, dot, dot. And you want to ask yourself, which of these is easier to compute? Is it easier to take this number and cut it in half? I can just do that in my head, right? I'll get 0.70710 something, right? Or is it easier to do this thing? This is some long division, right? I barely remember how to do that. I think I'm supposed to write something like 1.4142135 dot, dot, dot. And then over here put like a 1 and a bunch of zeros. And then do some sort of mechanical thing here to get that. So this is hard. This is easier. But nowadays, guess what? We have calculators and we have very easy ways of figuring out what the square root of 2 is. So there's no need for us to go around and memorize things like that the square root of 2 is 1.4142135. How many of you even knew that? If you didn't know that, then there was really no benefit in writing the square root on the top instead of on the bottom. So in this class, as it should be in all classes from now on, you should be perfectly happy writing a square root in the denominator. However, if you don't like it, write it in the numerator. I mean, that's fine. We will understand and we'll be able to convert from one to the other. So these 3 examples were very heavy on the algebra. Now we're going to switch to something completely different and look at derivatives where we don't have any formulas at all. Look at them completely graphically.